Professor Miley, can you talk about what it's like working in the condensed matter nuclear science that has really come of age since the internet and is now a global effort across international lines, and where there's so many collaborations internationally?
Thank you. Good question, but let me jump back a little bit. When cold fusion was first announced and caused such a commotion, and then many people criticized Pons and Flashman, and it became quite a negative thing, criticism. The community decided that they would hold many of their meetings outside of the U.S. because that would free them from hopefully the mounting criticism which seemed to be unjustly put against them here in the U.S. So if you look, the international meetings on cold fusion, ICCF, have been going on, well, I don't know, maybe every year and a half or so, and they rotate between Italy, Europe, various places in Europe, Russia, upcoming ones in Korea. These meetings have brought together international scientists because it's, the field has become international for this very reason. So that happened independent of the internet. The internet has helped communications, and so this is either good or bad, depending upon what your goals are. I mean, international collaboration is great because of the the abilities and the new insights you get from others elsewhere. But on the other hand, this is a competitive world, you know, global economy, all that stuff. And many of us, myself included, would like to see the U.S. be the first to develop this field. But because of this situation, it may be well it's first developed commercially elsewhere. In fact, Rossi and Greek people have said they have commercial units already. And if that turns out to be true, there's some debate about it. But anyway, this may be commercialized someplace else. And much of this gas-loaded nanoparticle work was initiated in Japan. And so you would have to assume they may be ahead too. So it's also competitive as well as collaborative. That's just the new world we have.
You probably missed Professor Solani's talk today at CERN.
Yes.
I happened to catch that on the webcast. He actually called for an international program to fund this research on a much larger scale and begin development of a technology from the science. Do you think that an international program could work, and what might be the first steps to creating such a program to develop this science?
Before addressing that, let me say one nice thing that has happened. It's quite recent. I don't know if people know about this. University of Missouri received money to create an institute for LNR science, and so that's a great start. That's the first at a university. I will put a plug in for Illinois and maybe myself. Some years back, I had through some quirk of getting some money from somebody, created a scholarship for undergraduates in LNR. So I've been supporting, trying to get interest built up in the field locally, but that's small scale compared to what we're talking about. An international institute might be good. I don't know if it's necessary in that this is a very commercial field. Most people now are getting into it because they feel that the technology will, if it becomes commercial, create great money and at the same time change the whole energy scene. And so it's very competitive. Normally international collaborations like CERN or like International Tokamak and so on are working on something that's not game-changing and hence not as threatening as this could be if somebody else beats you to it, which would make an international group awkward, I think. I'm not sure how well they would collaborate because of each country's worries about losing this technology. But in principle, it would be great.
Fabulous. Let's put this here. It's been 23 years since Drs. Fleischmann and Pons made their initial announcement of a new form of energy that would be clean, cheap, and abundant. Now it's very clear that this reaction is, in fact, real.
Mm-hmm.
What do you say to skeptics today that are still saying that this is a fraudulent claim? What do you have to say to them?
Well, I wholeheartedly disagree that anything was fraudulent. Certainly, Drs. Pons and Fleischmann, and I've known both personally, and they are great scientists. The whole web of events that caused what I think they would agree was a premature announcement to the public that caused all this storm of emotions that grew was just unfortunate, and any personal ramifications on the individuals is so unfortunate. But that's happened to many people in the field. The field has had a series of tragic events occur where workers in it have been maligned, and all that's just unfortunate that emotions grew so high. This should have been done in a scientific fashion, and I think that would have been so much better for everyone concerned. But I have nothing but the highest respect for Dr. Pons and Fleischmann, such great scientists. Anyone would be privileged to follow their lead in science.
Mm-hmm.
Okay.
Let me get this. Can you talk about when you first heard the initial announcement? What were your first reactions?
It's very interesting. Actually, quite a interesting history for me personally in that. At the time, I was editor of the Journal of Fusion Technology, and one day, as I was trying to get some papers in my office put in my briefcase to take a flight to Japan, the phone rang, and it was Steve Jones from BYU. And Steve was a good friend of mine. We'd worked on some muon catalyzed fusion stuff in the past and what have you. And he said, "George, I have this paper about cold fusion I'd like to publish in your journal, but I don't know if you would accept it since does your journal cover cold fusion?" And I said, "I don't know what cold fusion is, but Steve, I know you, and if you think it's fits in, please send it to me and I'll have it reviewed." And I said, "I have to get on, I'm late to get to the airport. I have to leave immediately. I'll be back in a week and I'll have this paper handled by reviewers. So I got on the plane, and when I got off, I was greatly surprised by my hosts, who were from University of Tokyo, came waving the equivalent of the Wall Street Journal, or I guess it was, saying, "What is this cold fusion? You're an American, you must know all about it." And I said, "My gosh, if I'd only taken time to ask Steve what it was, I could answer your question." So that was my introduction.
And when you first then learned more about what it was and what Doctors Fleshman and Pons were talking about, what did you think?
Well, I guess I didn't worry about that because, let me put it this way, when I got back to my office, suddenly there were 5 students in the hall waiting for me. It was a week later, who wanted to do experiments. Now, I first was so excited thinking, well, all these students want to work with me. But then I realized I happened to, for other reasons, have more heavy water than anyone else in the university. So they wanted to use my heavy water. But they did want to work with me too. But anyway, I'd never seen such excitement. And so I wasn't so thinking about all of this in what fashion you're talking about. I just said, okay, if this excites my students like that, I'm all for it. Let's find out what it is. And so then I tried to pore over the facts I got, which had famous facts that was some way released to their paper that went prematurely around the world. And the facts, by the time it got to me, was so mutilated I had trouble reading it. But I tried to understand it best possible. And my type of work I do, I usually don't like to repeat someone's work. My purpose, my thinking was not to try to repeat what they'd done, but try to think of some other alternate way of doing it. And being a plasma type person, thoughts that raced through my mind were, what we have to do is load palladium some way. Why not load it with plasma, deuterium plasma, rather than electrolytically, since I didn't know anything about electrochemistry. I learned later, but I didn't. So anyway, so those were thoughts. So my thinking was entirely different from, saying, well, is this what they've done, is that correct or not? My thinking was, well, this is really exciting, let's find out what's there. Now later, I had the privilege, although I don't know it turned out to be exactly a privilege, I did testify in the first congressional hearing on the subject. I was the only one who hadn't done any work in it. The congressional aide had asked me to testify. I said I was an unbiased, innovative researcher, and they wanted one of those stuck in between some of the people who were arguing. Mm-hmm. And so I ended up between Harold Firth, who was head of Princeton Plasma Physics Lab. I happen to know him well since I worked on fusion plasmas. He testified that this whole thing was all a big mistake, that cold fusion would never work and couldn't replace hot fusion. And Martin Flashman, who I spoke next, and then Martin Flashman, because they wanted me between these two warring parties. And Martin Flashman chided Firth, saying, we've already accomplished break-even. So he was something to think about. He was claiming excess heat. That means you get more energy out, and he was claiming fusion reactions, more energy out by fusion reactions than you put in. And Princeton was still trying to get there, and of course, we're still trying to get there with hot plasmas. And the two of them then, with me sort of standing by, not saying much of anything, got into a huge argument about that. And both are extremely, Furf unfortunately has passed away, but they are extremely articulate British debaters. And so if you go back to that testimony, I was just fascinated listening to them argue this case. It was like I was in a debating society again. So these are my memories.
Oh. Were your first experiments after hearing about the announcement? Did you actually put the a deuterium plasma into on a palladium chunk?
Okay, you're getting into interesting territory. Well, so by this time I also came up with this concept with my good friend Heinz Hoare, who's professor of theoretical physics in University of New South Wales. We developed a swimming electron layer theory, and I decided to make multi-layer thin films on a plate and hit that with a plasma generated by plasma focus. And so I thought that was going to really be a great experiment. What happened was, as soon as I hit it, all the films fell off. They couldn't take the plasma heating, and so we ended up with nothing. And I reported that and discussed it with Martin Flashman, who said, "Well, that was a very clever experiment. You just have to think about it harder, George." Martin is I really like him. He's always
humorous.
Yeah. And very, I don't know, he gets to the issue.
Well, after your plasma infused film fell off, what was your next step? Because clearly you've continued to research this over the years. Something kept you going. What was it?
Well, I mean, that was just a technological setback. Anyone who's in science hits those, had problems like that before, so that doesn't stop you. You just try to find out how to get around it. So I was working on that. A little bit later, I ran into Jim Patterson. And people may not remember all this. He had the so-called Patterson cell, which he was interviewed on Good Morning America or something about he was going to have a great fusion system. His was quite different from what, again, the original Pons Flashman type. And so his system was a packed bed flowing electrolytic system. It had coated plastic beads. These beads were coated with thin films. Well, he electrolytically coated them with, they weren't really that thin, they were sort of thicker coatings of nickel or maybe nickel palladium or something. And these beads were very small, millimeter diameter things. And he'd put a few thousand of those in a vessel and run the electrolytic fluid through them. And they formed, being metal, one of the electrodes. And the other electrodes worked into the container. And you could measure the temperature rise of the fluid going through, measuring the temperature came in and the temperature came out of this thing. Knowing the flow rate of the fluid, you could figure out how much heat went into the fluid to heat it up. If you knew how much electricity you were putting in for electrolysis, you know how much you were putting in from external power, and subtract that to find out if there's excess heat. And he was very successful in many of those early experiments. But when I saw him first time in a meeting, I saw a picture of these beads, and I said, those look like an inertial confinement fusion target, which is nothing, that's a hot fusion device I haven't done before. And I said, I know how to make those beads. And so anyway, it turned out that I thought I did, but I didn't. But I convinced Jim that what I should do is plasma deposit thin films on the beads like I've been working on. Because I realized suddenly that he had solved my problem. That is, these beads were such that they were a plastic, and so when the films either expanded by heating or loading, when you load a palladium, it expands by a factor of, well, not quite 2 or something, a tremendous change in it. And so you can picture if you have a thin layer of palladium on something, just when you load it with deuterium, the expansion is going to cause it to change volume relative to whatever it's sitting on, and that'll tear it off. But the bead is so fantastic because it bonded to the bead, and then when it expanded, the plastic gave. It was, you know, it wasn't a solid substrate, and that allowed it to work. Jim didn't realize that, and I don't know, I realized it first, but it dawned on me that I could coat these beads with thin layers like I'd been doing on the other metal surfaces, but this would work. So started on that. Well, long story short, I continued working with him and also his grandson, Jim Redding, who had gone to business school and had founded the company SETI, which the granddad was the chief technologist in, and the grandson was running a company. And they were going to make these. In fact, they had a contract with a hot water heater company to put these in. I took some of his beads and the ones I finally made, and incidentally it took me a year to figure out how to do this. That's why I said I wasn't as smart as I thought I was. And when I looked at mine under a scanning electron microscope to see how the structure looked on mine versus the ones he made, and mine really looked great. I had put on a perfectly uniform film with virtually no scratches or defects or anything in it. His looked horrible. Electroplating, it had all sorts of, looked like mountains on Mars or something on the surface. Terrible. And so I used some of mine in one of his devices, and they scarcely worked at all. And so that was another setback for me personally, thinking, here I've done all this work to make perfect films, and they don't work, but Jim's do. Explain that. Well, it finally, some years later, began to dawn on me, and this reinforced the thought that I expressed earlier about voids and so on. You don't want perfect films. I was making a big mistake. You want lousy ones that have all these defects in them, because that's where the reactions take place. And Jim had sort of stumbled on that. And but he hadn't realized what it was then either. And although he had observed hot spots, melted spots on his beads too, I mean, all this sort of fit together. And unfortunately, Jim had made a bucket of these beads, and later when he discovered he had used them all, he tried to make another batch, and the second batch didn't work right. And so non-reproducibility plagued him, and his and then his grandson died a premature death of a heart attack, and I don't know, Jim, well, sort of went out of business after all that, after all these blows. So it was a very sad everything. He was a brilliant person. I'm going to go.
Okay. All right.